You know that water you are drinking right now holds secrets that have puzzled and fascinated scientists for centuries. Water, or H2O, is much more than just a simple liquid. It's a molecule with a unique set of properties that makes life on Earth possible. Today we are going to uncover the incredible chemistry behind water, and trust by the end of this video you will never look at the glass of water the same way again. Hello science enthusiasts, welcome back to the SWA, where we explore the mysteries of molecular biology, biophysics, biosensors, and radiation. I am Ayub Basiri, and today we are diving into one of the most fundamental yet fascinating substances on our planet, water. Whether you are a seasoned scientist or just someone curious about the world around you, this video is for you. Let's start by looking back into the history of water study. Water has been essential to life since the dawn of time. Ancient civilizations such as those in Egypt, Mesopotamia, and Greece not only relied on water for survival but also viewed it as a sacred element. The Greek believed that water was one of the four fundamental elements alongside the earth, air, and fire. However, it wasn't until the 18th century that we begin to truly understand the composition of water. The breakthrough came with scientists like Henry Cavendish, who first identified hydrogen as a distinct element in 1766. Later, Antonio Lavoisier, often called the father of modern chemistry, demonstrated that water is not an element, but a compound of hydrogen and oxygen. This revelation was a turning point in the history of chemistry and led to the chemical equation we all know today, H2O. Water's story is not just one of scientific discovery, but also of how it has shaped human civilization. The availability of fresh water has determined the location of cities, influenced agriculture, and even sparked wars. Understanding water's chemistry helps us appreciate not just its role in our daily life, but its influence on the course of history. Now let's dive into the chemistry of water. Water is compound of two hydrogen atoms bonded to one oxygen atom, forming a molecule that's been at an angle of about 104.5 degrees. This angular shape is crucial because it gives water its polar nature. But what does it mean for water to be polar? In simple terms, the oxygen atom is more electronegative than the hydrogen atoms, which means it pulls the shared electron closer to itself. This creates a partial negative charge near the oxygen and partial positive charge near the hydrogen. This polarity is what allows water molecules to form hydrogen bonds with each other. Hydrogen bonding is one of the water's most fascinating properties. These bonds are relatively weak compared to covalent bond or ionic bond, but they are strong enough to give water its unique characteristic. For instance, hydrogen bonds are responsible for water's high surface tension. You have probably seen this in action when you fill a glass of water slightly above the rim and notice that the water doesn't spill over. That's surface tension at work, keeping the water molecule tightly bound together. Another important property of water is its density. Most substances become denser as they cool and transition from a liquid to solid, but water behaves different. As water cools and approach its freezing point, the molecule arrange themselves into crystalline structure that is less dense than liquid water. This is why ice floats on water, a phenomenon that's crucial for aquatic life in cold environment. If ice sank, bodies of water would freeze from the bottom up, making life impossible for those environments. Actually, in Arctic and Antarctica, thick layer of ice is on top of water because of that, and beneath them actually filled with liquid water. And it's important that the water could not go below 4 degrees of Celsius. It's beautiful because the ice by itself is act like an insulator and prevent the heat exchange between the air in the atmosphere and the liquid water below the ice caps. Water's polarity also makes it an excellent solvent, earning its the it the title of the universal solvent. It can dissolve a wide range of substances, which is why water is essential in biological process, whether it's dissolve salt, sugars, gases, and every other molecules. Water's ability to interact with other molecules is vital for life. Let's take a deeper look into how the discovery of water's composition unfolded. In the late 18th century, the scientist community was buzzing with experiments related to gases. Henry Cavendish, a British scientist, made a significant contribution by identifying inflammable air, or what we now call hydrogen. Cavendish observed that when hydrogen burned in air, it produced water, but he didn't fully understand the chemical reaction at play. It was Antoine Lavoisier, a French chemist, who clarified this process. Lavoisier conducted experiments that demonstrate water was not an element, as previously thought, but a compound of hydrogen and oxygen. In 1783, Lavoisier and his colleague Pierre-Simon Laplace conducted an experiment in which they passed a spark through a mixture of hydrogen and oxygen, producing water. This experiment not only confirmed water's composition, but also laid the groundwork for the law of conservation of mass. Lavoisier's work was revolutionary. It helps shift the scientific understanding from ancient idea of water as a fundamental element to modern view of it as a compound. This discovery was fundamental in the development of modern chemistry and marked the beginning of a more systematic approach to studying chemical reaction. Water unique property make it indispensable in various fields. In biology, water is the medium in which most cellular processes occur. In facilities, the transport of nutrition, the removal of waste, and the regulation of temperature with living organisms. In fact, about 60% of human body is water, highlighting its importance in maintaining life. In chemistry, water's role as a solvent is unparalleled. It's involved in countless reactions from the solution of salt to the hydrolysis of complex molecules. Water is also used in titration process where its ability to dissolve a wide range of solutes allows for accurate measurement of chemical concentration. Industrial water is used in variety of processes, including cooling in power plant, cleaning, and as a reactant in production of chemical. In agriculture, water is the lifeblood of crops, and irrigation practices have been developed to optimize water use in farming. Additionally, water is crucial in the production of food and pharmaceutical and countless other products. In energy production, water is a key compound in hydroelectric power, where the kinetic energy of flowing water is converted into electricity. Moreover, in nuclear reactor, water acts as both a coolant and neutron moderator, essential for maintaining safe and efficient operations. Now let's delve into some more advanced concepts related to water. One intriguing property is water's high specific heat capacity. This means that water can absorb a lot of heat without significant rise in temperature. This property is due to the hydrogen bond between water molecules, which requires a considerable amount of energy to break. The high specific heat capacity of water plays a crucial role in regulating Earth's climate by stabilizing temperatures in ocean and other large bodies of water. As I mentioned, hydrogen bonding is pretty weak, but because we have a lot of them in a cup of water, it could actually act like a gigantic force which prevent water to increase temperature rapidly. Another fascinating aspect is water's role in the structure and function of protein. Proteins are workhorse of the cells, and their function depend on their 3D structure. Water molecules interact with amino acids that makes up protein, helping them to fold into correct shape. Without water, proteins would not be able to maintain their structure or function properly. It's good to mention that when proteins want to fold, actually water make a cage around the protein and force hydrophobic chains into depths of the protein, and hydrophilic chains of protein could come out of depths and present on the surface of protein. This is how protein folding works. In addition to its biological importance, water is also involved in some of the most crucial chemical reactions on Earth. One of these is the process of photosynthesis, where plants use sunlight to convert carbon dioxide and water into glucose and oxygen. This reaction not only provide energy for plants but also produce the oxygen we breathe. It's good to mention that this process not only occurred on trees. The main source of oxygen we breathe is the cyanobacteria on oceans and seas. Let's continue. Water is also unique in its ability to participate in acid-base chemistry. Pure water can dissociate into hydrogen ions H plus and hydroxide ions OH negative, which makes it both a weak acid and a weak base. This self-ionization is a rare property and is essential for maintaining the pH balance in the biological system. In fact, the pH scale itself is based on the concentration of hydrogen ions in water, with the pure water having a natural pH of 7. Imagine we add something acidic. Acids actually could release H positive in the environment. We increase the H plus or H positive in the environment or in our solution. This could imbalance the amount of hydroxide and hydrogen ions, could shift from 0 to 14 scale, which 0 is extremely acidic and 14 is extremely basic. In acid solutions, we have a lot of H positive ions, but in base solution, we have OH negative ion. Let's continue. In summary, water is a molecule that defies expectation. Its simple structure belies a complexity that is crucial to life, chemistry, and the environment. From its unique density and surface tension to its role as the universal solvent and its involvement in life-sustaining process, water is truly a remarkable substance. The next time you take a sip of water, remember the incredible property that makes it so essential. If you are as fascinated by water as I am, and if you have any question or topics you'd like me to explore in the future videos, please leave a comment below. I love hearing from you, and your ideas could inspire the next episode. And of course, don't forget to like, share, and subscribe to SWA for more deep dives into wonders of science. Until next time, stay curious and keep exploring the amazing world of science.